this gives us an approximation for the relative intensities for multiple peaks. Okay, and if you know how this works, you can actually draw your own Pascal's triangle. Write it on napkins in McDonald's and things like that, just to freak people out. Nevertheless, this gives us an approximation for how those peaks will look. So if I have a quintet, I'll have a 1 to 4 to 6 to 4 to 1 ratio. The peaks on the outside are very small because why?
The likelihood of occurrence really low.
Yeah, the likelihood of having 4 hydrogens next door all aligned the same way is low. And so that's why on a relative basis, the peaks on the perimeter of the multiplet are very small because they represent the extreme states. The ones in the middle represent various combinations that are much more probable. And Pascal's triangle helps us predict that. Okay, the distance between the peaks in the multiplet is what we call a coupling constant. Is that on this slide? It's not. But it turns out, well, let's go back here. Let's see if we've got what we're talking about here is this distance between this peak and this peak. And it turns out if these hydrogens are being split by these hydrogens, the splitting distance between them would be the same. There's a reciprocity going on here. And that distance is called the coupling constant. And so in a high resolution NMR, which would be associated with what kind of a magnetic field?
Would be like strength, really strong.
A strong one. Remember, like a 300 megahertz system, I can actually see enough separation on the spectrum where I can actually measure the distance. And I can say, these hydrogens are splitting with these hydrogens because the distance is the same. You understand what I'm saying? And so we're talking about that effect here, the splitting distance. It's called, again, the coupling constant. Some general rules here. Protons that are identical don't split each other. Protons bond to the same carbon generally will split each other only if they're non-equivalent. We'll see how that can happen. Protons on adjacent carbons do split each other, and protons that are splitting each other have the same coupling constant. Long-range coupling we don't see. So here's this guy. With its hydrogen, it's not going to couple with that guy. Where will we see that happen? We had, last year we saw an exception from last semester. An aromatic rings. Because of the close association, because of the resonating double bonds on an aromatic ring, carbons 2 apart, the hydrogens on them do couple with one another separately. That's what we'll see. And that's why you'll very often see very messy looking multiplets coming out of benzene ring. Because you've got coupling upon coupling. Like here. You can see this peak is not a nice clean peak. In fact, how many different kinds of equivalent protons are present on this benzene ring? There are 3. There's this kind, which is right next door to the ethyl group that's attached. There's this kind, which we say is beta to the ethyl group, and there's this kind that's para. And so we've got 3 kinds of hydrogen here. And those 3 kinds of hydrogens are splitting each other, both next door and long range. And so we see a real complex pattern. In general, for this reason, we usually don't try and pick apart the aromatic ring, the hydrogens on the aromatic ring. We say, there's 5 of them there. I've got a benzene ring with one thing attached to it. That's usually about as far as we go with it. Over here, these 2 hydrogens and these 3 hydrogens are going to split. This is going to appear as a triplet, which is right here. You just barely see it. This guy is going to appear as a what? Quartet. Notice that there are no hydrogens at this position on the ring. So this guy only sees 3 neighbors, so they will appear as a quartet. These guys see 2 neighbors, so they'll appear as a triplet. And what can you say about the splitting distance from here and here?
Match.
Should be the same. Is Remember, hydrogens that split each other split the same distance. And again, that's called the coupling constant. Here's splitting for an isopropyl group. This hydrogen here, there's only one, is split by 6 immediate neighbors. And so it's going to appear as a heptet. Okay, and you can see it blown up here. 1, 2, 3, 4, 5, 6, 7. Now, there's one thing I should tell you about, and I mentioned it, I'll stop after this. I know this has been a lot today. These multiplets lean toward each other. I don't know if I've told my class in the fall that they do that. But notice this thing is not perfectly symmetrical. Can you see that? Yeah, it's skewed or leans toward the right-hand side. Yeah, it will align itself, it will skew itself toward the hydrogens it's coupling with. Do you understand what I'm saying? And so I look at these guys, will appear as a doublet. Notice the doublet's not perfect. The one to the other side is more pronounced. In general, multiplets will lean toward the ones that they're coupling with. So if you can't measure coupling constants, you can use the leaning. Leaning is probably not the right word, but they're skewed toward the side that they're coupling. Does that make sense? And so I can say this guy here is skewed towards something upfield. This guy is skewed to the downfield side. And you'll see that is a very repeatable, very commonly observed effect. All right, enough damage.